Imagine pressing play on the universe. You'd see not a handful of galaxies, but around 2 trillion vast islands of stars, gas, and dark matter spread across the observable cosmos. Most of them, about 90%, are so faint, so distant, or so buried in dust that no telescope humanity has ever built can see them. We live at the shore of a cosmic ocean, staring across a dark surface, knowing that almost everything that exists lies just out of reach. Today, we're going to fly through that ocean. We'll explore galaxies that are dead but still spinning, giants that stretch for millions of light years, rings and eyes and polar structures that look impossible, and newborn galaxies from the dawn of time that shouldn't exist, yet do. Welcome to Galactic Briefing. Buckle up! The universe is much stranger than it looks from here. 1. How many galaxies are there really? For a long time, astronomy textbooks repeated a comforting number: 100 billion galaxies in the observable universe. It was a big number, big enough to feel infinite, but it was also wrong by about a factor of 10. In 2016, astronomers took ultra-deep images from the Hubble Space Telescope and turned them into 3D maps of the universe at different ages. Then, they added in the galaxies that are too faint and too far for Hubble or any current telescope to detect directly. The result was shocking. The observable universe appears to contain around 2 trillion galaxies. If you tried to count one galaxy per second without ever stopping, you'd still be counting more than 60,000 years from now. And we only see about 10% of them. The rest are beyond our detection limits: too small, too diffuse, too ancient, or too redshifted by the expansion of space for their light to reach us in any recognizable form. So when we say universe, we're really talking about a vast structure where almost everything is hidden. 2. Why the night sky is dark. With so many galaxies, you might expect the night sky to be blazing bright from edge to edge. An old question, known as Olber's paradox, asks exactly that. If space is full of stars in every direction, why isn't the sky as bright as the surface of a star? The answer is a mix of several cosmic tricks. The universe isn't infinitely old. There hasn't been enough time for all the light to reach us. Space itself is expanding, stretching light to longer, redder wavelengths until it fades beyond what we can detect. And much of that light is absorbed and scattered by dust and gas along the way. So yes, in almost every tiny patch of sky, if your eyes were powerful enough, there would be galaxies, sometimes hundreds stacked along that line of sight. But the expansion of the universe and the finite speed of light keep most of that glow locked away, turning the heavens into a mostly dark dome pierced by a few nearby stars. 3. The big 3 galaxy types. To navigate this cosmic zoo, astronomers group galaxies into 3 main families: spiral galaxies, flat disks with graceful arms; elliptical galaxies, smooth, featureless balls of stars; irregular galaxies, chaotic shapes that don't follow any neat pattern. Think of these as the basic architectural styles of the universe. Spirals. Our home, the Milky Way, is a barred spiral galaxy, a central bar of stars with arms winding outward like a cosmic whirlpool. Those spiral arms aren't solid structures. They're density waves, regions where gas and dust are compressed, sparking bursts of star formation. The arms glow blue because of hot, young stars that live fast and die quickly. Roughly 60% of galaxies are spirals, and about 2/3 of those have bars cutting across their centers. Bars act like galaxy engines, funneling gas inward and feeding both star formation and central black holes. Ellipticals. Elliptical galaxies are the opposite. No arms, no disks, just a smooth ball of mostly old red stars. They contain very little gas or dust, which means almost no new stars are forming. They can be tiny dwarfs with a few million stars, or giants with trillions of stars spread across hundreds of thousands of light years. Many form when spiral galaxies collide and their orderly disks get scrambled. Irregular galaxies. Irregular galaxies look like someone shook a galaxy until it fell apart. They're often small, lumpy, and asymmetrical, packed with bright star-forming regions. Many are satellite galaxies orbiting larger systems, distorted by intense gravitational forces. In the early universe, irregulars were much more common. Over time, mergers and interactions transformed many of them into spirals and ellipticals. 4. Dead galaxies. When the lights go out. Galaxies are alive as long as they're forming new stars. When that process stops, the galaxy is effectively dead, even though its existing stars will shine for billions of years. Here's the twist. For a long time, astronomers believed that dead galaxies had to be ellipticals, messy leftovers of violent collisions. Then they found galaxies like MAX 2129-1 and XMM 2599. These are dead disk galaxies. They still have a disk structure and coherent rotation like a spiral, but almost no gas and no new stars. Their stars formed early in a furious burst, and then the fuel supply was cut off. No major merger, no obvious catastrophe. Just a galaxy that stopped. What killed them? A central supermassive black hole may have blasted out enough energy to blow away or heat up the remaining gas. Or the galaxy might have simply used up its gas so efficiently that there was nothing left to form new stars. Fast forward the universe tens of billions of years into the future, and most galaxies will look like this: quiet, red, and fading. 5. Giants. Galaxies on monster mode. At one extreme of the size scale lie ultra-compact dwarfs, tiny galaxies just a few hundred light years across, containing maybe a few million stars. At the other extreme are monsters like IC 1101, a giant elliptical galaxy sitting at the center of a massive galaxy cluster. IC 1101 is estimated to be up to several million light years across and may contain over 100 trillion stars. If you swapped the Milky Way with IC 1101, its stars would extend beyond the orbit of Andromeda and deep into what is now intergalactic space. These giants grow by cannibalizing their neighbors over billions of years. Smaller galaxies fall in, get torn apart, and add their stars to the central giant's halo. Embedded within is an enormous supermassive black hole with a mass tens of billions of times that of our sun. Yet, ironically, these titans can look ghostly faint. Spread those stars across such an enormous volume, and the galaxy becomes diffuse, more like a low-glow city skyline than a blinding stadium floodlight. 6. Collisions and cosmic cannibals. Galaxies are not static, isolated islands. They pull on each other, collide, merge, and sometimes flat out eat their neighbors. Here's the strange part. When two galaxies collide, almost no individual stars collide. The distances between stars are so huge that they pass through each other like two swarms of bees intermixing. What does collide is gas clouds, which crash together, compress, and ignite starbursts. Dark matter halos, whose gravity shapes the entire merger. Famous colliding pairs like the Antennae galaxies or the Mice galaxies show long, dramatic tidal tails, streams of stars and gas flung outward by gravity. Our own future is already scheduled. The Andromeda Galaxy is on a collision course with the Milky Way. In about 4.5 billion years, the two will merge into a new giant galaxy, often nicknamed Milkdromeda or Milkomeda. The odds of our sun actually hitting another star are tiny, but our orbit around the new galactic center could change dramatically. On smaller scales, galaxies act as predators. The Milky Way is currently tearing apart the Sagittarius dwarf galaxy, its stars wrapping around us in long streams. The large and small Magellanic clouds visible from the southern hemisphere are likely destined to be eaten as well. Look far into a galaxy's halo, and you'll often find stellar streams, the fossil remains of galaxies that were devoured long ago. 7. Dark matter, the invisible skeleton. If you add up all the light from stars and gas in a galaxy, and then measure how fast that galaxy rotates, something doesn't match. The outer parts are rotating too fast. Based on visible mass alone, they should have flown apart long ago. The missing ingredient, everything you know, every city, forest, ocean, mountain, and person is built from matter that was born in the first seconds after the Big Bang. Every star in the sky, every planet circling those stars, every atom and every drop of water. Even the water on Earth is ancient. The hydrogen atoms in it were forged moments after the universe itself came into existence. Only later did everything else follow. 1. The moment everything began. The Big Bang is not just a theory, it's the defining event of our universe. Inside that first moment are the answers to our deepest questions. Why are we here? Where did we come from? Does the universe have a beginning and an end? If yes, what are they like? To search for these answers, humanity has built machines the size of cities on Earth and telescopes that orbit high above it. When we look deep into space, we are also looking back in time. As we peer farther and farther away, we see the first newborn galaxies, the first stars lighting up the darkness, the universe in its infancy. Push far enough and we arrive at the very beginning, the moment the universe itself switched on. And there we confront the ultimate questions in physics. What actually banged? Why did it happen? And what, if anything, existed before the Big Bang? We don't yet have final answers, but each new observation brings us a little closer. 2. A universe that refused to stay still. A little more than a century ago, scientists believed the universe was static and eternal. It simply existed, unchanging on the largest scales. Then, in 1929, everything changed. At the Mount Wilson Observatory in California, astronomer Edwin Hubble measured the light from distant galaxies. He discovered those galaxies were not fixed in place. Almost all of them were moving away from us. The farther away a galaxy was, the faster it was receding. A galaxy twice as far moved away roughly twice as fast. 3 times as far, 3 times as fast. This relationship became known as Hubble's law, and it was the first solid evidence that the universe is expanding. If everything is moving apart today, that means in the past, everything must have been closer together. Run the cosmic movie backward, and galaxies crowd together, distances shrink, temperatures soar, until everything we can see collapses into a tiny, hot, dense state. That is the birth of the universe, about 13.8 billion years ago. Even without telescopes, you can experience this idea whenever you look at the stars. Light from a star 1 million light years away takes 1 million years to reach you. So you're seeing it as it was in the distant past. In principle, if we could gaze far enough, we would see the earliest moments after the Big Bang. The Hubble Space Telescope, named after Edwin Hubble, was launched for exactly this reason, to look deeper into the universe, and therefore deeper into time, pushing our view as close as possible to the cosmic beginning. 3.
Where did the Big Bang take place? One of the first questions people ask is, where did the Big Bang take place? Over there? Over here? The surprising answer, it happened everywhere at once. In the beginning, the universe itself was incredibly small. The Big Bang wasn't an explosion in empty space, it was the rapid expansion of space itself. Every point in today's universe was once part of that tiny, dense state. Then comes the more difficult question. What came before the Big Bang? How can something arise from nothing? Ancient philosophers puzzled over this idea. Modern physicists do too. What's astonishing is that the laws of physics suggest that under certain conditions, something really can come from what looks like nothing. It's one of the biggest hurdles to understanding the Big Bang. To accept it, you have to accept that our entire universe, everything we see and care about, all matter, energy, space, and time, could have arisen from a state that we might describe as nothing. We cannot truly describe this moment in everyday language. All we know is that we go from almost nothing to near infinite density, near infinite temperature, near unimaginable violence. And from that fireball, the universe begins. 4. The violent birth of Earth. Fast forward billions of years from the Big Bang to the birth of our solar system. About 4.6 billion years ago, a cloud of gas and dust around the young sun began to clump together. Within that swirling disk, tiny grains collided and stuck, forming larger bodies called protoplanets. The young Earth at this stage was round, had an iron core, and had a rocky surface, but it was much smaller than today, only a few hundred miles across. It had to grow 4,000 times more massive, and it had a lot of competition. Thousands of protoplanets were zooming through the solar system, colliding at over 20,000 miles per hour. This was a brutal cosmic demolition derby. Evidence of that ancient violence can still be found on Earth today. In Arizona, the famous meteor crater was formed by an impact just 50,000 years ago. The rock that caused it, however, was 4.5 billion years old, a relic from the era when planets were still forming. Some of these rocks are incredibly rich in iron and nickel. They likely formed deep inside the cores of early protoplanets that were later shattered by collisions, scattering their interiors into space as meteorites. This chaotic time has a dramatic name, the Titanomachi, the War of the Titans. Every rocky world, including Earth, went through this. Some protoplanets were completely destroyed. Others collided and merged, growing into full-size planets. The strongest survivors ate their neighbors and dominated their orbits. After tens of millions of years, the dust began to settle. What remained were a few strong planets: Mercury, Venus, Earth, Mars, and a fifth world, Theia, a Mars-sized body on a deadly trajectory. 5. The collision that changed everything, Theia and the Moon. Theia hurtled toward Earth on a path that could have destroyed our planet completely. A head-on impact might have shattered Earth into rubble, leaving only an asteroid belt behind. But fate tilted the angle. Instead of a direct impact, Theia delivered a glancing blow. Still the most violent event in Earth's history, but not quite total destruction. The consequences were staggering. Earth's surface was melted again into a deep magma ocean. Huge amounts of rock were blasted into orbit. Enough material was thrown out to build a mountain as wide as the United States and 10,000 miles high. This debris formed a wide ring around Earth. Over time, gravity pulled that ring into clumps that grew into 2 small moons. For millions of years, Earth may have had 2 moons dominating the night sky. Eventually, those moons drifted together and merged into one, the single large moon we see today. Our moon is unusually massive compared to Earth, so unusual that we are nearly a binary planet, and that has huge consequences for life. The moon's gravity keeps Earth's axis tilted at a relatively stable angle. That stability creates regular seasons and a climate pattern that life can adapt to. Without such a large moon, Earth's tilt might wander wildly, producing extreme climate swings that would make complex life much harder to sustain. Thanks to our distance from the sun and the stabilizing moon, Earth is not permanently frozen, Earth is not permanently boiled. Instead, we have liquid water, the key ingredient for life as we know it. But that water had to come from somewhere. 6. Something from nothing. The quantum vacuum. Before we follow the water, we return once more to the beginning. How did the universe come into being, people ask? Surely you can't get something from nothing. We don't want the answer to be a trick. We want a real explanation. But the truth is, we don't yet fully understand the physics of the earliest moments of the universe. To get clues, physicists study empty space. But does empty really mean nothing is there? Surprisingly, no. In quantum physics, the vacuum is not truly empty. It's a restless sea of quantum fields, fleeting particles and antiparticles, electromagnetic fluctuations. Particles can spontaneously appear and annihilate again, emerging and vanishing too quickly to see directly, but leaving effects we can measure. Space is full of these virtual particles constantly popping in and out of existence. In this sense, nothing is actually something. Even in the quietest possible state, the vacuum has energy. Some ideas suggest that a large, random fluctuation in this quantum vacuum could generate enough energy to trigger a Big Bang, the birth of a new universe. If that's true, then our universe might not be unique. There could be a vast multiverse, an
1. Standing at the edge of time. Close your eyes for a second and picture this. You're standing on a cosmic shoreline, looking not across an ocean, but back through time. That's essentially what NASA did when the James Webb Space Telescope locked on to a tiny smudge of light astronomers call something like MOM Z14. Names are not its strong suit. This galaxy lived just 280 million years after the Big Bang. On a 1 year equals all of cosmic history calendar, that's January 2nd. The universe has basically just stopped being on fire. And yet, this thing is already blazing with millions of young stars. Webb's instruments split its light into a spectrum, like a barcode of the universe, and found it had been stretched by the expansion of space to 14 times its original wavelength. That huge redshift tells us this is baby universe territory. The galaxy is tiny, only a few hundred light years across, hundreds of times smaller than the Milky Way, but way too bright for its age and size. Something inside it is burning through gas and forming stars at a pace that standard physics really doesn't like. Then comes the real curveball. Its light contains carbon and oxygen. Those elements don't come from the Big Bang. They're built inside stars, then scattered when those stars explode. That means in the first 280 million years, multiple generations of stars have formed, lived, died violently, and seeded new stars with heavy elements. That's an entire cycle of stellar life and death before the universe has even celebrated its 300th millionth birthday. 2. The oldest wall we can see. So, how far back can we actually look? There is a hard limit, a kind of cosmic wall, not made of rock or gas, but of light itself. About 380,000 years after the Big Bang, the universe went through a phase change called recombination. Before this, space was a glowing, dense plasma of electrons and nuclei. Photons bounced around constantly. Light couldn't travel any real distance. Then the universe cooled to about 3,000 degrees C. Electrons finally settled into orbits around protons, forming neutral hydrogen.
Suddenly, light was free to move. That ancient light has been traveling ever since, stretched by expansion into a faint microwave glow only a few degrees above absolute zero. We call it the cosmic microwave background, the CMB. If your eyes could see microwaves, the night sky wouldn't look dark. It would be filled with a soft, almost perfectly uniform glow with tiny temperature ripples, differences of about 1 part in 100,000. Those ripples are baby blueprints for everything, slightly denser regions that gravity would later turn into galaxies and clusters. But here's the catch. No telescope will ever see past this surface with light. Before recombination, the universe was opaque. That era, those first few 100,000 years, is permanently hidden from us in ordinary light. To probe earlier, we need totally different messengers. Gravitational waves, neutrinos, not photons. The CMB is the oldest photo we will ever take of the universe. 3. The impossible black holes. Fast forward a few 100 million years beyond that wall. James Webb starts finding galaxies that already host supermassive black holes weighing millions, even billions of times the mass of our own sun, when the universe is less than 1 billion years old. Here's the problem. Black holes grow by eating gas, dust, stars. But there's a physical speed limit called the Eddington limit. Feed them too fast, and the radiation from the hot, infalling gas pushes new material away. It's like trying to pour water into a cup while blasting it with a hairdryer. Even if a tiny black hole started right after the Big Bang and ate at the maximum rate, it still shouldn't reach the insane masses we're already seeing that early. So how on Earth, how in the universe, did these monsters grow so fast? Astronomers are seriously considering a wild idea: heavy seeds. Instead of starting from dead stars a few times the sun's mass, some black holes might have formed when giant, pristine gas clouds in the early universe skipped the star phase entirely and collapsed directly into black holes, already weighing tens or hundreds of thousands of suns at birth. That solves the timing problem. Start big and you don't need as many frantic growth spurts. Then Webb turned up something even stranger. Galaxies where the black hole mass and the galaxy mass are backwards. In normal modern galaxies, the central black hole is about 1/1000th of the galaxy's stellar mass. But in some early systems, like those nicknamed black hole first galaxies, the hole dominates and the galaxy is just a faint, struggling halo around it. It's as if the engine came before the car. The black hole forms first, and the galaxy gradually assembles around it. And if, as that wasn't enough, Webb found a black hole that looks like it's laughing at the Eddington limit. In a small, early galaxy, one black hole appears to be feeding at up to 40 times the supposedly maximum allowed rate. 40! How? Maybe the accretion disk is thick and puffy, letting radiation escape out the poles while matter keeps pouring in from the sides. Maybe the gas falls in as dense clumps, giving gravity a brief advantage before radiation ramps up. Or the black hole is spinning so fast that it warps space and changes how light pushes on matter. Whatever the exact mechanism, the message is clear. In the early universe, black holes didn't always obey the neat rules we wrote later. Webb has also seen pairs of supermassive black holes, millions of suns each, already in spirals, on their way to merge, less than 1 billion years after the Big Bang. That means 2 galaxies had to form, each had to grow a massive black hole, those galaxies had to collide, and their central black holes had to sink together, all in a tiny fraction of cosmic time. When they finally merge, they send out gravitational waves powerful enough to briefly outshine the light from all the stars in a galaxy, except in gravity instead of light. 4. Monsters that break the rules. And as if that wasn't enough, Webb found a black hole that looks like it's laughing at the Eddington limit. In a small early galaxy, one black hole appears to be feeding at up to 40 times the supposedly maximum allowed rate. How? Maybe the accretion disk is thick and puffy, letting radiation escape out the poles while matter keeps pouring in from the sides. Maybe the gas falls in as dense clumps, giving gravity a brief advantage before radiation ramps up. Or the black hole is spinning so fast that it warps space and changes how light pushes on matter. Whatever the exact mechanism, the message is clear. In the early universe, black holes didn't always obey the neat rules we wrote later. Webb has also seen pairs of supermassive black holes, millions of suns each, already in spirals, on their way to merge, less than 1 billion years after the Big Bang. That means 2 galaxies had to form, each had to grow a massive black hole. Those galaxies had to collide, and their central black holes had to sync together, all in a tiny fraction of cosmic time. When they finally merge, they send out gravitational waves powerful enough to briefly outshine the light from all the stars in a galaxy, except in gravity instead of light. 5. The first stars and the longest night. Go back even further, into a universe where there are no galaxies, no stars, no visible light, just cooling hydrogen and helium gas and dark matter silently shaping the cosmic skeleton. This era is called the Cosmic Dark Ages. Dark matter slowly pulls gas into dark matter halos. For tens or hundreds of millions of years, nothing shines. The universe is transparent but empty of light. Then somewhere around the 100 or 200 million years after the Big Bang, something changes. Gas in the densest halos collapses far enough, gets hot enough, and the first stars ignite. These population 3 stars were nothing like the Sun, made almost entirely of hydrogen and helium with virtually no heavier elements. Much more massive, often dozens or hundreds of times the Sun's mass. Incredibly bright and short-lived, millions, not billions of years. Without metals to help gas cool and fragment into many small stars, the early universe built fewer, bigger giants. Their ultraviolet light carved glowing bubbles into the surrounding hydrogen, starting the slow end of the cosmic dark ages. When these giants died, many detonated as titanic supernovas, forging and ejecting the...
Right now, as you listen to my voice, there might be another version of you hearing a slightly different sentence. In a universe you will never visit. Not science fiction, not a movie plot, but one of the most serious possibilities in modern physics. In the last few decades, scientists have uncovered something extraordinary. Quantum reality might constantly split into parallel histories. A hidden shadow universe could be overlapping our own, invisible to light but heavy with gravity. And we may already be using those other realities every time a quantum computer runs an algorithm. Welcome to Galactic Briefing. If you enjoy exploring the weird edge where physics starts to sound like philosophy, consider subscribing. Now, let's step into the multiverse. 1. When reality refuses to pick just one outcome. At everyday skills, reality seems boringly solid. A mug is either on the table or on the floor. A cat is either awake or asleep. You can't be at work and on vacation at the same time. But zoom all the way down to the quantum level and the rules stop behaving. Electrons, photons, atoms, the tiny building blocks of everything, don't sit in one definite place. Instead, they spread out like a probability fog, existing in all the allowed positions at once. Physicists call this a superposition.
Until something is measured, a particle doesn't choose. It isn't here or there, it's both here and there, in a clear, precise mathematical sense. The equations that describe this fuzzy reality work unbelievably well. They predict experimental results to ridiculous accuracy, far beyond what any other theory in science has ever achieved. But there's a catch. The moment you measure the particle, the moment you ask it a question like, "Where are you?" the fog of possibilities seems to collapse. Suddenly, one result appears, one position, one outcome. And that raises a haunting question. What happened to all the other possibilities that were real a microsecond earlier? Did they vanish? Were they never real in the first place? Or were they go somewhere else? 2. The dangerous idea. What if nothing ever collapses? For many years, the standard answer was, don't worry about it. The math works, just shut up and calculate. But in the 1950s, a young graduate student named Hugh Everett refused to shut up. He asked a deceptively simple question. What if there is no collapse at all? Instead of the wave of possibilities suddenly snapping to a single outcome, Everett proposed a radical alternative. The quantum wave never collapses. All outcomes remain real. The universe simply splits into branches where each outcome happens. In one branch, the particle goes left. In another, it goes right. Both branches are equally real, but now they can no longer interact. This became known as the many worlds interpretation. At first, almost everyone hated it. It sounded extravagant, wasteful, almost mystical. Infinite universes just to explain a single measurement. But the brutal truth is, Everett wasn't adding anything weird. He was doing the opposite. He took the standard quantum equations, refused to bolt on a mysterious collapse, and just followed the math to its logical conclusion. And the math says, quantum superpositions don't vanish. They simply decohere into separate, non-communicating branches. Which means every quantum event doesn't choose a future. It creates all of them.
1. High-level summary, in plain language. This documentary answers the question, what is the edge of the universe? By explaining that, the universe probably has no physical edge, like a wall or border. What we really hit are limits of observability and causality. The observable universe, how far light has had time to reach us. The particle horizon, about 46.5 billion light-years away. The event horizon, about 16 billion light-years. Beyond this, light emitted now will never reach us. It shows how expanding space, dark energy, cosmic horizons, inflation, dark matter, and quantum physics shape what we can see, what we can never see, and what might exist beyond our cosmic bubble. It closes on a philosophical note. The edge tells us more about the limits of knowledge and our tiny perspective than about a literal boundary of reality. 2. Structured outline of the documentary. You can think of this as episode chaptering for a YouTube script. 1. What do we mean by edge of the universe from 00 to 330? Universe equals everything observable plus unobservable. Edge equals limit of information, not a wall. Introduction to the observable universe. Diameter 93 billion light-years. Farthest galaxies we currently see are 46.5 billion light-years away. Looking far in space is looking back in time. James Webb's deepest galaxies, universe less than 400 million years old. Approaching the cosmic microwave background as the ultimate wall of light. 2. Expansion of space, no center, no edge, from 330 to 750. Debunking the explosion from a point picture of the Big Bang. Big Bang equals expansion of space itself, not an explosion into pre-existing space. Raisin bread and expanding dough analogy. Every galaxy sees every other receding. No center in 3D space. Hubble's law. Galaxies recede faster with increasing distance. Redshift as evidence that space is stretching. The universe as a cosmic web. Galaxies, clusters, voids, and filaments. Same physical laws everywhere. Hydrogen, helium, gravity, light. 3. Observable universe versus whole universe from 750 to 1650. Observable universe, defined by how far light has traveled since the Big Bang. Why we can see things 46.5 GOY away even though the universe is only 13.8 billion years old. Space expanded while light was en route. Distinction. Particle horizon equals what we can see now. Event horizon, approximately 16 GOY, equals what we will ever be able to see. CMB as the photosphere of the universe. Universe was opaque until 380,000 years after Big Bang. After recombination, photons travel freely to CMB today. Other possible messengers beyond the CMB. Cosmic neutrino background, approximately 1 second after Big Bang. Primordial gravitational waves, fractions of a second after Big Bang. 4. How we measure the universe, from 3230 to 3955-ish, block. Cosmic distance ladder, parallax for nearby stars. Standard candles. Cepheid variables, distances to nearby galaxies. Type 1a supernovae, distances across billions of light years. Redshift distance relation, using Hubble's law and Ferdman equations. Other tools. Surface brightness fluctuations, Tully-Fisher and Faber-Jackson relations, gravitational lensing as a mass and distance probe, baryon acoustic oscillations, or BALO, as a standard ruler, CMB angular scales to constrain geometry and expansion, Hubble tension, local measurements, about 73 kilometers per second per megaparsec, CMB-based measurements, about 67 kilometers per second per megaparsec. Possible explanations. Unknown systematics, early dark energy or new physics, modified gravity, unknown particles. 5. Cosmic horizons, particle, event, and Hubble sphere, from 26 to 3130. Particle horizon, current radius, about 46.5 GOY. Edge of what has ever sent us light. Event horizon, about 16 GOY, in co-moving distance. Events beyond this can never affect us. Hubble sphere, distance where recession speed equals speed of light, about 14 GOY. Not a true horizon, light can still escape from beyond it given cosmic history. Future. As dark energy dominates, more galaxies drift beyond the event horizon, leaving only the local group to empty our sky. 6. Dark energy, why expansion accelerates. From 48 to 5620. Discovery via distant Type 1a supernovae in 1998. Dark energy equals 68% of the universe. Negative pressure equals repulsive gravity. Cosmological constant as a simplest model. Alternatives, quintessence, dynamic scalar field, modified gravity, early dark energy, etc. Long-term implications. Heat death if dark energy stays constant. Big rip if it grows stronger. And big crunch if it reverses. Vacuum decay or false vacuum bubble as a quantum doomsday. 7. Inflation and the pre-Big Bang picture, from 5638 to 10439-ish. Inflation equals ultra-rapid expansion in less than 10 to the power of negative 32 seconds. Solves for horizon problem, CMB uniformity, flatness problem, why universe appears flat,
Monopole problem, why we don't see predicted relic particles. Quantum fluctuations stretched to cosmic scales, seeds of galaxies and structures, primordial gravitational waves to possible B-mode signal in CMB, eternal inflation and multiverse, our universe as one bubble among many. 8. Geometry and topology, shape of the universe, from 104.39 to 108.41. Curvature options, flat, closed, sphere-like, or open, saddle-like. Current data, space is very close to flat. Topology, even flat space can be finite, for example, 3 torus. Searches in CMB for repeated patterns show no evidence of small closed topologies. No universe must be larger than observable patch. 9. Dark matter, invisible scaffolding, from 135.12 to 142.20. Evidence. Galaxy rotation curves, Vera Rubin. Cluster dynamics, Zwicky. Gravitational lensing, CMB power spectrum, 27% dark matter versus 5% normal matter. Candidates, WIMPs, axions, sterile neutrinos, primordial black holes. Role and structure, dark matter clumps first to halos, baryons fall in later to form stars and galaxies. Cosmic web emerges from dark matter skeleton. 10. First stars and galaxies, edge of time, from 129.04 to 135.12-ish. Cosmic dark ages after recombination, population 3 stars, massive, metal-free, short-lived. Cosmic dawn and reionization. UV from first stars and galaxies reionizes hydrogen. Reionization finished by Z6. JWST's role. Galaxies at Z10, even 13 plus. Challenge to standard models, early massive galaxies, early SMBHs. 11. Gravitational waves as a new probe, from 221.09 to 227.35. LIGO Virgo, stellar black hole and neutron star mergers. LISA and future detectors, supermassive black hole mergers, possibly early universe phase transitions. Gravitational waves can probe epochs inaccessible to light, pre-CMB, independent Hubble constant, via standard sirens. 12. Multiverse and extra dimensions and exotic ideas, from 142.45 to 220.34. Multiverse variants, eternal inflation to bubble universes, string landscape 10 to the power of 500 vacua, many worlds quantum interpretation, brain universes in higher dimensional bulk, extra dimensions from string theory and brain worlds, observational constraints, LHC, gravity tests. 13. Fate of the universe, edge in time, from 148.41 to 156.44. Big freeze or heat death if L constant. Big rip if phantom dark energy. Big crunch or cyclic models if gravity eventually wins. Vacuum decay or false vacuum bubble as a quantum doomsday. 14. Quantum entanglement and information, from 208.44.
Far from the reach of sunlight, the universe is almost unimaginably cold. Out between the stars, where no planet glows and no atmosphere stirs, space falls to just a few degrees above absolute zero. There is no wind, no sound, only dust and ghostly particles drifting from millions of years. A lone starship crossing this abyss feels nothing on its hull, but a constant, gentle sandblasting of atoms moving in slow motion. Ahead, in that black ocean, lies a faint red ember, a dim dwarf star whose light takes more than 4 years to reach us. That star is Proxima Centauri, our nearest stellar neighbor.
Beside it orbits Proxima b, a rocky world that has become the symbol of our first true step into interstellar space. 4 light years sounds modest when spoken aloud, but it's a distance that breaks our everyday language. We measure it in light years because kilometers lose their meaning. How do you carry fragile human beings across such a gulf? Which engines can turn centuries into decades? What designs whisper of travel measured not in lifetimes, but in weeks? Tonight, imagine we follow those paths one by one. Generation ships that take 400 years, fusion vessels that cut the journey to decades, exotic concepts, laser sails, antimatter, warp bubbles that, on paper, compress the crossing to days. Leaving the sun's protection. Near Earth, space feels almost gentle. Our star wraps us in a protective bubble of charged particles, a vast flow of solar wind that carves out a region called the heliosphere. Inside this invisible cocoon, cosmic radiation is softened, electronics degrade slowly, and the sun's presence still shapes our environment. But any ship bound for Proxima b must eventually reach the edge of this shelter. Out there, the solar wind thins and collides with the rarefied gas between stars. The sun's influence fades. Interstellar space begins. There's no shout, no shockwave at this frontier. When Voyager 1 crossed it, there were no alarms. Its sensors simply began to detect more energetic particles from beyond the solar system and fewer from the sun. That change marked a one-way threshold. On the far side, space is older, colder, and far less forgiving. Solar panels become almost useless. Radiation shielding is no longer optional. It is permanent infrastructure. Communication delays lengthen from minutes to hours, then to years. A mission to Proxima b must plan to live in this environment, not for months, but for decades. Inside the heliosphere, failure can still be a shared problem. Engines malfunction and ground control can help. Beyond it, every serious crisis must be solved on the ship itself. Navigation, repairs, medical care, power systems, all must function without real-time assistance. Interstellar space isn't a wall. It's a test of whether a spacecraft can become an independent world. At 1/10 of the speed of light, even a dust grain the size of a sand particle hits like a bullet. On impact, it explodes into plasma that can gouge metal, fry circuits, and puncture vital systems. Cosmic rays, atomic nuclei moving near light speed, born from ancient supernovae and violent galactic events, slip through holes, flipping computer bits and slicing through human DNA. Cells can repair some damage, but beyond our sun's shield, the rate of injury rises faster than evolution prepared us for. Every extra kilogram of shielding improves survival, but also slows acceleration. Interstellar travel is a constant negotiation between speed and safety. We don't leave our star because we underestimate these dangers. We leave because exploration has always demanded that we step beyond familiar protection into landscapes we don't yet know how to endure. Distance as time, not just space. 4 light years is not just a line on a map. It is an enormous span of time. A beam of light leaving Earth for Proxima Centauri does nothing dramatic. It doesn't carve a trail or ignite the darkness. Second after second, it slips through a ghostly haze of gas and dust. Even at nature's speed limit, it needs more than 4 years to arrive. A spacecraft is slower. At 100 kilometers per second, far faster than any crewed mission flown so far, Proxima b is still tens of thousands of years away. At 1% of light speed, the trip shrinks to roughly 400 years. That's already longer than the entire history of modern science. This space between stars is not like an ocean dotted with islands, nor a wilderness with landmarks. From a ship's windows, the view after 1 year looks almost identical to the view after 20. The stars barely shift. Progress is something you don't feel. It's something you calculate. Navigation becomes an exercise in inference. You don't watch mountains pass by. You watch tiny shifts in starlight frequency and position, measuring your motion against the background of the galaxy. Communication, too, loses its familiar rhythm. A question asked from Earth might take over 4 years to reach a ship near Proxima, and another 4 for the answer to come back. Conversations stretch into something closer to archaeology. By the time you receive a reply, the moment that prompted the question has already become history. In this sense, the emptiness between here and Proxima b is defined less by what fills it and more by what it lacks. No resupply, no quick return, no nearby safe harbor. Everything you need to fix, grow, feed, heal, and decide must travel with you or be created on board. The void is not hostile the way a storm is hostile. It simply offers no help. To plan a journey like this, you must treat 4 light years as a time span, not a distance. You're not designing a route. You're designing a long, unbroken era of survival. The 400-year generation ship. Picture a rotating starship, vast and slow, spinning to create artificial gravity. Inside its curved decks, fields of wheat and vegetables bend with the hull. Artificial skylines mimic dawn and dusk. Children learn to walk under a gentle centrifugal pull that feels like home. This is a generation ship, a vessel that doesn't race, it endures. Its engines gradually push it to around 1% of light speed, turning the journey to Proxima b into a 400-year crossing. No one who boards will ever see the destination. Babies will be born who never see Earth. They will grow up under metal ceilings, their world defined by rotating corridors, greenhouses.
Far from the reach of sunlight, the universe is almost unimaginably cold. Out between the stars, where no planet glows and no atmosphere stirs, space falls to just a few degrees above absolute zero. There is no wind, no sound, only dust and ghostly particles drifting from millions of years. A lone starship crossing this abyss feels nothing on its hull but a constant, gentle sandblasting of atoms moving in slow motion. Ahead, in that black ocean, lies a faint red ember, a dim dwarf star whose light takes more than 4 years to reach us. That star is Proxima Centauri, our nearest stellar neighbor. Beside it orbits Proxima b, a rocky world that has become the symbol of our first true step into interstellar space. 4 light years sounds modest when spoken aloud, but it's a distance that breaks our everyday language. We measure it in light years because kilometers lose their meaning. How do you carry fragile human beings across such a gulf? Which engines can turn centuries into decades? What designs whisper of travel measured not in lifetimes, but in weeks? Tonight, imagine we follow those paths one by one. Generation ships that take 400 years, fusion vessels that cut the journey to decades, exotic concepts, laser sails, antimatter, warp bubbles that, on paper, compress the crossing to days. Leaving the sun's protection. Near Earth, space feels almost gentle. Our sun wraps us in a protective bubble of charged particles, a vast flow of solar wind that carves out a region called the heliosphere. Inside this invisible cocoon, cosmic radiation is softened, electronics degrade slowly, and the sun's presence still shapes our environment.
But any ship bound for Proxima b must eventually reach the edge of this shelter. Out there, for as long as humans have looked up at the night sky, we've wondered the same thing. Are we truly alone? And where did our own life begin? Today, many scientists, including teams at NASA, believe that the chances of life existing beyond Earth are very high. The universe holds billions of planets, and it would be strange if ours were the only world where life took root. But there is an even more astonishing idea. What if life on Earth itself began with ingredients delivered from outer space? Seeds of life from the stars. In a recent study published in Nature Communications, researchers confirmed that meteorites, rocks from space, may have carried vital building blocks of life to our young planet. We know Earth formed around 4.5 billion years ago. In its early days, it was a hellish world, constantly bombarded by meteorites, comets, and debris. The surface was far too hot and unstable for life to exist. Life seems to have appeared later, roughly 4 billion years ago, in our planet's ancient oceans. These seas were rich in organic material, a kind of chemical soup where molecules could collide, link together, and grow more complex. Over time, they learned to use energy from sunlight and water and give rise to the first primitive living cells. At the heart of this transformation are two extraordinary molecules: DNA, the molecule that carries genetic information, and RNA, its sister molecule, crucial in the first stages of life. But there's a deep mystery. Where did the original building blocks of DNA and RNA come from? For years, some scientists argue that these components might have formed elsewhere in the universe and then been delivered to Earth by interstellar meteorites. At first, this idea didn't convince many people. Careful analysis of space rocks had only found 2 of the 4 main bases used in DNA. That changed when scientists at Hokkaido University in Japan developed a more refined method to study meteorites. They analyzed 3 space rocks that had fallen in the United States, Canada, and Australia. This time, they found additional DNA components in all 3 samples. In total, they identified 5 key nucleobases, the core ingredients necessary to build DNA and RNA. This discovery suggests something incredible. The chemical bricks needed to start life may have existed before Earth itself was fully formed. Meteorites may have acted like cosmic delivery ships, bringing the seeds of biology to our world. We already know that some of Earth's earliest water might have come from comets and icy bodies. Now the essential ingredients of DNA and RNA appear to share the same kind of origin. All of this supports a bold idea. Life on Earth may have been started, or at least boosted, by materials from deep space. And if meteorites could sow the seeds of life here, they could do the same on countless other planets. On worlds with stable climates, oceans, and energy sources, those seeds could grow into living ecosystems, perhaps even intelligent civilizations.